All right, so on page 8 we have examples 4 and 5. 5 I told you I wasn't really in love with, but we'll do it anyway. When I say I'm not in love with a problem, then you can pretty much rest assured that it won't be on a test. So, but it's not terrible. It's just not my favorite problem in the world. Right? So, use areas to evaluate the integral of the square root of 4 minus x squared dx. All right, so let's think about what that means for a sec. Just this guy. So that's some function f of x, right? But forget about that. Let's just call it y. Under the root. Now, we're supposed to use areas, which would imply that we're not just typing it into the calculator, which means that we're using some sort of geometry concept. Right? That radical there is kind of in the way, so let's square both sides and see what happens. We get y squared equals 4 minus x squared. Whenever you have two variables raised to the second power within an equation, you're most likely looking at a conic section. Right? So that's your ellipses and circles and things like that. In this case, it's actually the simplest case. In this case, it's the simplest case. That's nice. I'm going to add x squared to both sides. And we will be looking at x squared plus y squared equals 4. All right, that's a circle. So we could draw a sketch. That circle has a center at 0, 0, and a radius of 2. Man. All right. Because it's only the positive radical, we're only looking at the top half of that circle. And you can verify that just by popping it into your calculator. You just take a look and see f of x or y equals the square root of 4 minus x squared is just the top half of the circle. All right, you only get plus or minus. I may have mentioned this last class, but it's just so many different courses that I never know what I mentioned anywhere. You only get a plus or minus if you're the one taking the square root, if you put the square root in there. If it was already there, it's whatever sign came with it, standard equipped. All right, so this is a semicircle. The area of a semicircle is 1/2 pi r squared, which would be 1/2 pi times the radius, which is 2, squared, which is 2 pi. All right. If you use the integral function in your calculator, so math option 9, type in all this stuff and hit enter, you get 6.28 roughly, which is your 2 pi. All right. Oh, just by counting boxes. Oh, you mean to draw it to begin with, or from the drawing? Oh, the draw. It's always the square root of whatever the constant is. All right, so you may be wondering, what's the deal with the geometry? Why do we have to worry about stuff like this? Well, when you're dealing with certain types of volumes, the only way, and that's what we're going to be moving towards, the only way you could actually get an appropriate integral to get that volume would be to know the appropriate geometry formula for things like triangles, circles, semicircles, which is just half a circle, so just chop it in half. Rectangles and squares you shouldn't have any trouble with. It's when I throw an isosceles trapezoid at you, you're like, all right, I might need a second on that one. But it comes to you anyway at some point.
So why did you put
Because it was only the positive root. Positive root is the top half of the circle. Negative root is the bottom half of the circle.
So if it's at negative rad 4 minus x squared, it would be the bottom.
It would be the bottom, and you'd have a negative 2 pi as your final answer. Yeah. Right. Yeah, and you got to be careful about that, because if you take a geometry approach, let's say you actually draw just the bottom half. This had a negative. You drew the bottom half, ignore the top half, rightly so. You looked at it and said semicircle, pi r squared divided by 2, got an answer 2 pi. Remember, an antiderivative over an interval is asking for a net area. Right? So that's talking positive areas and negative areas. Those are all fair game. It's when it asks for a total area, that's when you drop the negatives. Right? So if it's the bottom half, you got to know, if you're using a geometry approach, you got to know to slap a negative onto that result. The sign of the, yeah, so if it's a positive radical to begin with, the top, negative radical, it would be the bottom. Yeah, if there was nothing there, I just shoved it in there. It's like 2 is a positive 2, you don't have to write the positive. You know.
it's not question. This is about total.
It's not about total area.
Or
It is, unfortunately, it is absolutely crystal clear that it is about a net area. And that is because an antiderivative over an interval, a definite integral, gives net area. All right? And that's a fact that you need to know. An antiderivative over an interval, so a definite integral, gives a net area in all circumstances. Sometimes that net area is negative, sometimes it's positive, but it gives you the net area after the interval is completed. Right? The only times, there's 2 situations in which you'd be asked for a total area. So any ambiguity, any uncertainty is net area. If they say, find the total area, that's obvious. If they give you, this is what I was talking about last class, if they give you a pre-printed graph, and they say find the area, that's when you need to know that you're also looking for total. So this one's kind of along the same line. We're looking for a net area, again, because we're given a definite integral. So what we need to do is get a picture here. In order to get a picture, it might behoove us, I guess, to take a look at this function and see what's going on here. All right, so absolute value of x is the same as plus or minus x. Now, I'm not limiting your use of the calculator as a support tool, so you can take a look at the graph in its original form if you want. I'm just assuming you want to at least get a sense of the underlying structure. All right, so this would reduce down to y equals plus or minus 1. All right, so we're looking at 2 lines, y equals 1, y equals negative 1. All right, that's what I'm getting to. So, looking at the function itself, we have to make the statement of the caveat. Anytime we have a restriction on our domain, we make a note of that. So, does not exist at 0, where, so, semicolon, x not equal to 0. All right, so that's a little bit of an indicator for me. It's telling me that, okay, I obviously can't have y equals 1 and y equals negative 1 happening at the same time, because then it wouldn't be a function. It would fail the vertical line test. So they have to be happening one at a time. If there is a discontinuity at 0, that's telling me that's where the break is going to happen. It's just really a question of what's coming first. The negative stuff, you know, the y equals negative 1 or y equals positive 1. Right? So what we can do is just use a test value in the original function if you want. You could do something like, and again, at any point you can go to the calculator and take a look. But I could say something like y of -1. So I'm just going back to this guy. Would be absolute value of -1 over -1, which would just be -1. And then same idea, this time y equals 2. I'm just going with the lower bound and the upper bound of the interval. So upper bound is 2, lower bound is -1.
That would be -2.
That would be a negative.
Wait, the bottom one is the denominator is not -1?
No, because I'm going back to the original function. So absolute value of 2 over 2 would be a +1. Okay, so that's telling me that for values of x left of 0, it's -1. For values of x to the right of 0, it's +1. So I can get a sketch going. I'll make it a little wider. Alright, so we're looking at something on the low end, something along these lines. So closed interval. Ooh. Open circle here because it doesn't actually exist at that location. And then open circle because again it doesn't exist at that location. Going out to here. Alright. So then it's a question of, well, what would the encapsulated areas be? Alright, so I'm looking at this region and this region. Alright, so at this point I would use my knowledge of symmetry to pare it down a little bit, because this rectangle is equivalent to this would-be rectangle here, so I chop that off. Alright, so let me go red here. So these two guys cancel out. And then that remaining piece would actually be the only thing I would need to determine the area of in order to find my final answer. And that has a base of 1 and a height of 1. So the area, or the final answer, would be base times height equals 1. Intimidating.